Guys, welcome back to my YouTube channel. We're still under strength of material N6. Let us look at this slope and deflection. Today we'll be focusing on this simply supported beam with a concentrated load in the center. That means it's a point load. It's not a distributed. It's not a UTL. So we'll talk about slope and deflection. So in figure 4.26, shows us a simply supported beam with a concentrated load in the center there. So let's say you have a beam. We'll be introduced to that. As you have a beam, guys, here, I apply the point load there. You can say this is a point load, or you can use W if you want. You can use W, but that is a point load. You can even use W. Here we have your reaction at the end. Remember, simply supported, the reaction must be at the end. This weight will cause this beam to bend. Will cause it to bend. It will cause this to what? To bend like that. To bend. So we call this bending, that bend of that beam like that. We call it bending. It's a deflection. It will bend, right? The deflection, the change in that length there, we call this deflection. The change in that height, the bend there will be what we call that deflection. So as you can see, we have the theta there is is represented by a triangle, so it will bend obviously, as you can see there. So at the end you must check. At the end the slope is at the maximum. The slope here at the middle is equal to 0. If you try and take a line here, remember, if you take a line, you see the line will be straight. That means the slope there at the end is equal to 0. Here from the initial, if you take the straight line like this, you will see that the straight line there at the beginning, there will be some angle that will take place. If I take here on the hidden detail, where we have a hidden detail, let me look at this page. Sorry about that. We'll have here, you see the where you have your hidden detail there. Wanted to show you something there. See, if you take, you see the slope did not change. Initially the line is still straight. I can also put the line there below where the deflection is still straight. The line here, if I take a tangent, the straight line will still be straight. But however, initially here we have what? You see, I draw the straight line, we have the straight line. Then I take again the straight line on the hidden detail. On this hidden detail, I draw some straight line like that. If I draw the straight line there, you will see like this. You will see that there is an angle that will take place there. We have some angle there on the hidden detail. You see, you have the angle. So we have the angle. That angle, this angle there will be theta. So also we know alternative vertical angle. If you have theta here, also here we'll have theta according to maths. So you see we have what? The angle there between the initial point there. So that will be the slope angle. So but here we don't have angle between these things, guys. Simply just straight horizontal. So the slope here at the middle part at the center is equals to 0, but the deflection is maximum. Here there is no deflection. There is no deflection. It's still there. The deflection is equal to 0 here at the end. There is no deflection. There is no something like that. Deflection must be a curve. We don't have the curve there at the end. We don't have deflection. The deflection there, it is 0. All right. So how do we go about and calculate that deflection? So we have these formulas to calculate the deflection and the slope. Alright, we have the formulas. Here are the formulas that we use there. We have the formulas to calculate this slope is what it, as you can see, is equals to the weight multiplied by length squared divided by 16 multiplied by like that. This is a Young modulus. Also this is it's I, although that is not the length, it's I. My bad, that is I. This is I, moment of inertia multiplied by I. This is what it's I, the moment of inertia. Take note that it's I. It's how we calculate what the slope when they've given what the simply supported beam with a point load or concentrated load, not UTL, no, with a simply. Then how do we calculate the deflection? That deflection, depending on that bending, calculate that deflection using that formula there. We see that the deflection is W multiplied by length cubed 48. There, as you can see, we have there 48 times Young modulus of elasticity there multiplied by moment of inertia. This is how we calculate the deflection. Remember the point, the weight must always acting while in the middle of the what of the beam, must act there in the middle, always in the middle. So we'll use those formulas. So the limits can take place if you have such things like these ones, or this one is right. You see, the formula here can be used. Those formulas, these two formulas that we have here on the top, these two formulas can be used now. If the weight is acting exactly at the center, we'll use those two formulas. Must act at the center. But if we have 2 points load like this, we have the one that is acting in the middle, other does not act in the middle, the formulas cannot be used. This is a limitation. Also, if you have this scenario is not acting, we must have single one that acts in the middle, the formula cannot be used. It cannot be used. It's a limitation there. We're limited now. Alright, so we have this example here. We have the example is there on your textbook. So this example there, obviously we've given is 4.4. We've given a simple supported beam which is 4 meter wide long. All right, this is a simply supported beam, simple supported beam which is 4 meters long. From there till there, it's 4 meters long. You know it's supported there. It has a load 200 kilonewtons, situated exactly in the middle. I said must be everywhere in the middle, exactly in the middle here. Supposed to have there in the middle, which is 200 kilonewtons, which is good. Right, now we've given, they say we should calculate the slope and the deflection of the beam if the fluctual stiffness is 300 meganewton meter squared. These guys, EL, we call this the fluctuate, flexural stiffness. That is our flexural stiffness. It's AE combined. It's a Young modulus multiplied by moment of inertia give us this. So we have this there. All right. So we're supposed to calculate the deflection. As we apply this, remember there will be a deflection that will take place. I will show it with in detail. This beam will bend. There will be a deflection like that. So we want that deflection. There will be deflection. The change. We want that change. There will be deflection that will take place. So we're supposed to have that deflection. There will be a deflection. We have to calculate that deflection and the angle that will take place, that is a change in angle. So how we go about, we're using that from those formulas here, the ones that we have there, those two formulas. Now they are applicable, we should use them anyways. So all right, so we can apply those formulas, guys, because this is at the middle, we can use them. This is not a limitation. We can calculate our slope is given, we say it is W multiplied by the length. We square that length, we divide this by 16 multiplied by E multiplied by I. All right, so what is the weight? Obviously this will be a point load. Here is it 200, yeah, times 10 to the power of 3, since it's given in kilonewton, multiplied by the length is 4 meters of the beam, multiplied by 4. Obviously we have the squared there. Then we divide this by 16. All of these combined, we have given the multiplied by what? 300 mega. It's in mega, same as times 10 to the power of positive 6. So we punch this, supposed we'll obtain 0.889. all right. Oh, this is an angle, by the way. My bad, that is an angle, by the way. And then okay, that is an angle, and then this angle, okay, you see, this is an angle. Okay, that angle, this is an angle, by the way. This angle is measured, must be given in radians, will be in radiant. It's in radiant. Remember, it's in radians, like when we're dealing with shaft, those things, it's in radians. So the theta will be in radians. We'll have our angle there, which is 6,667 times 10 to the power of minus 4 rad. Given this in what will be in radians. All right, so this is the angle there. So we want now the deflection that will take place there. Supposed to have now the deflection. All right, the deflection is denoted by triangle. The deflection will be weight multiplied by length cubed. Now we'll have cubed there, divide by 48, multiplied by E, sorry about that, multiplied by our E there, multiplied by a modulus of elasticity. All right, then we're supposed to substitute the load. We still have 200 there, times 10 to the power of 3. The length is still 4. So now we cubed that length, divide by 48, multiply by this. We have given there is still 3, is multiplied by 300 times 10 to the power of positive 6. Still have this, therefore the deflection will give us 0.889 millimeter. This is our deflection. the change in that height a little bit there. When you're bending, we compare the original structure and then this change in that bending that will take place, we call that deflection. Remember, now we'll bend. Initially it's here. If we apply the load, will bend like this. We want this between these two. That is it. So that is it in this video. So in the next video, we'll be looking at UTL. If you've given UTL, how we'll go about, we'll find the deflection. We will get the deflection. How we go about to determine the deflection there, if we have the bending there. So thank you for watching. May you kindly subscribe to my YouTube channel if you have not subscribed, and click the notification bell so that you'll be notified whenever I post a new video.